Great. Can you see my screen?
Yes, we can see your screen.
Yes, we can see.
Great. Yeah, so as said, my topic is about parallelization and distribution of machine learning workloads to GPUs. And what we are talking about here is then this kind of semantics-free and in some sense mathematically sound approach based on something called APL and Vulkan. And so we can start by talking about programming languages. So in general, we could say that there are different kind of programming languages, and they kind of like try to focus on different things. So we might have performance, generality, and productivity. And regarding like maybe machine learning use case, and in the research, we are more focused maybe on MATLAB, Python, and Julia, so on the bottom side. But then if we go into like productive code, we usually start talking about OpenMP and C in the sense of generality, as these languages are usually meant for CPU processing. And then on the left side, we have more specific use cases or not so general use cases like maybe CUDA or FootHark, which are based on GPUs. So unless you have a GPU, you cannot use this. And then what I feel like is that if there would be something in the middle, it would look a lot like a hammer. Because once you would find a programming language which is very performant, productive, and general, it would kind of like, it would make everything look like a nail, because you would use it for all kinds of purposes. So whether that be maybe, say, web application development or machine learning or something like that. And I think maybe a lot of like what programmers usually talk about language wars and maybe kind of like differences in thinking regarding what is the best language come from the fact that people see the hammer in a different way. And then when we talk about edge computing and machine learning, what I've been thinking about is that maybe for that, the hammer would look more like a calculator. So it wouldn't be as general as the language would be more focused on kind of like scientific computing. And on the other hand, it necessarily doesn't have to be the most performant one, as maybe it's more about, especially in research areas, it's about productivity rather than, let's say, the best of the best performance. And then my recent research has brought me to this APL thing, which stands for a programming language. And I think it solves a lot of the problems, and it might not fit straight in the middle, but it's pretty good, I think, for machine learning. And I want you to know about it. So APL is restricted regarding generality, that it does only arrays. So it's a programming language, and the only data type is arrays. And regarding productivity, it's kind of like how you see it. It relies on these self-invented symbols to represent arithmetic about arrays and so forth. But it's surprisingly decent performance-wise, and in some cases it can even outperform C. And here's a video of APL, so let's see if you can hear the sound.
So if you like to look over my shoulder at some calculations, we'll have a brief look at APL. Let's start with something simple. Let's enter the expression 4.5 plus 6.3. If I press the carriage return, I get the answer. Now this illustrates one property of APL. Anything that I enter is indented. Anything that the computer returns is ranged left. So it's very easy to see whether you've entered something or whether the computer has provided the output.
So regarding that, it takes us back to 1960s. So APL is a very old language, as we can see from the video that it was used even when people programmed computers with typewriters. And it was invented by this guy named Kenneth Iverson at Harvard. and it was mostly about for teaching matrix algebra. So initially it wasn't even a programming language. But then it got turned into one when Iverson went working for IBM, and it became the canonical work for this branch of pretty, well, not well-known family of languages called array programming languages. And it was even a Turing Award-worthy invention. The idea was that, or the Iverson's argument regarding APL was that by relying on this very odd notation, what happens is that when you don't see something, you basically can focus on the problem more. When you don't have to think about software design, you can focus more on the actual problem. So that brings us to the main point of APL, which is something called rank polymorphisms, or recursion and loop-free semantics. So, and this is, I'm going to go through this quite quick, but it shows how APL works. So 1 plus 1 in APL is 2, but if you do 1 plus 1, 2, 3, 4, what you will get is an array in which the 1, the scalar value, is extended into an array. So basically the scalar value is lifted into an array automatically, and there is no loop or something like that you usually have to write. And you can do even matrices. So, and this shows that APL is also read from right to left. So what this says is that you have an 1 to 16 numbers or indices, which you reshape, which is that funny p, or yeah, and then it says that 4.4 times 4. So you get this kind of matrix as an output. And then you can do scalar operations on matrices. So adding 1, do that thing, gives you a matrix into which, on the which element or each element you add 1. And you can do something like a row-based sum reduction. So of that matrix, you can run this plus slash thing, and then you get each of the rows added together, and that kind of like decreases the rank from matrix into an array. And then it even supports cupoids. Cupoids are basically 3-dimensional arrays, and to any of these you can apply any kind of function. So you can write your own function in the brackets, and omega in this sense means the argument which comes from the right side. So a number in this case. And then you can say that, well, maybe you want to multiply it by 2, and you get back a cupoid in which each element is basically multiplied by 2. And then you can do even these very funny things, which I think are kind of like even a new concept to me as a programmer, that you can do views, or you can do binary matrices of different data structures. So here we do basically the remainder of each of the elements of that cupoid. And because the cupoid is from 1 to 16, you get this kind of 3-dimensional array. And then you can even reshape it as in one command to back to an array. And then you can do the sum operation on the array, and on the cupoid, and the matrix, and the vector, and the scalar. And you see that basically the same program flow which you write works regardless of what is the dimension of the your basically data structure. And basically the question you might ask is that, so what? And regarding this, I will go through very fast into then implementing APL in Python languages for machine learning. So you might have heard about this thing called scikit or NumPy for Python. And the thing how this works is that it starts from this function, which calls this function. And here we only think about this function. It calls this function. And here, the relevant part is this part, in which we read from the bottom to top. So for each E in the self-estimators, in here we are doing a random forest prediction. So pretty simple use case in that sense. Anyhow, for each of that random forest estimator, you run accumulate prediction function onto which you pass these 4 arguments. And then you run into this thing, which does this thing. And this thing is now this thing, because this is a function and not just some argument. So we get into this function. And this function calls, like more importantly, this thing. And it brings us to this thing. And now we just, in the Python level, we say that, oh, we don't even know what happens after this thing. But what actually does happen is that Python now calls C, so it switches from Python into something called Cython, which is this mix between Python and C. And the actual predict function looks something like this. And here we only think about this, we will get into the apply part. But this is just to show basically that you have a lot of boilerplate. You have this thing coming from something called self-value, and the self-values come from something called value and the array, from something called setState method, which gets us to, and after that we get to the actual apply function, which usually calls apply dense. And in the apply dense you actually get this is the actual prediction algorithm for the random forest tree. And as we can see, we have gone through a lot of code in order to get straight into there. And we will get into these in the slides, but basically the relevant part is that after some more kind of like confusion, we are able to get these 2 APL functions. So this is APL code, and we don't have to understand these 2 in depth right now. But what we can see is that in APL, we are able to represent, this is the Cython part of the code. So it's in 3 lines. And the other part after that, there's a small mistake, but you have to trust me on this. All the other Python code that we saw regarding like the ifs and elses and the stuff in there are represented by this thing. So basically these 3 lines and this 1-liner, they combine the whole random forest prediction algorithm, which gets us all the way back to here. And why I feel like that is more interesting is that we get into this kind of well, in the case we have this kind of a problem in which it is very hard even for someone in software engineering to understand what is actually happening in machine learning. And if we then start thinking about even this Cython and scikit library more in depth, what we can see on the left side, which is the Cython code, is that even though we run this on many threads, what we run is a while loop. And while loops are sequential. So in sense, even if you would have, say, 60 cores, when you run into a while loop, what will happen is that you can only do 1 element at a time. And so this is very kind of like surprising even to me that in this kind of very optimized code, we can find sequential code, even though we are trying to run it in parallel. But of course, APL has all these answers to this regarding like these so-called tree transformations into matrices. So very recently, there has been some work regarding data structures of reforming tree structures into matrices. And it's kind of and in APL in specific, because in APL in general you don't have while loops, and because APL does not support explicit looping or explicit recursion. And in this case we still found something called while in APL, but it comes from these extended libraries. But in general it would tell that if we have to use a while loop in APL, it means that we are doing something wrong. And that something wrong is not to the kind of mind of an APL programmer in APL in itself, but it's in the data structure. So if we need an explicit loop or recursion in APL, it would mean that our data structure is in fact wrong. So it brings us to this kind of a notation, or maybe a revelation that, okay, we have parallel hardware, but sequential software. And could maybe APL or some of these other languages or any language avoid the programmer of writing sequential software in order to make these edge computing and machine learning use cases faster? And our revelation is that what APL can teach is that even if APL is not the fastest thing, or it does not have the fastest compiler or interpreter, in some cases we can win performance by just avoiding explicit recursion. And if we believe to the thoughts of Iverson or the person who even invented APL, this is then being achieved by the fact that we now have more mental capacity because we have gotten rid of the pad notation. So this helps us to think about the actual mathematical problem in a better way, because we don't have to deal with the kind of like software architecture anymore. And now this brings us to this another thing, that APL runs very well on GPUs. And it's something what I've been now working on is that, well, basically I decided to make APL run on a GPU. And it was an extension to this paper of me and Jukka earlier, and in which we basically saw that for GPUs there exists this kind of language called Spiro5. It's kind of like an assembly language, and it can do interesting things. And the most interesting thing, at least for me, was that the fact that there's a very low cold start times, regardless of whether you're running it on a mobile device or a desktop computer. And it shows that an application migration can happen in milliseconds if you can just encode your software in Spiro5 for the GPU. And for application regarding like, well, especially like graphics, the UI device delay latency can be reduced a lot, because you don't have to anymore communicate necessarily the graphics. You can just communicate the Spiro5 commands. And this is like a very, very fast deep into like what I've been then working on, is that when you think about GPUs, you have to understand that there are different ways of doing it. And here we are talking about something called Spiro5 and then Vulkan. And together these two things make things fast. And basically Spiro5 is something that runs on Vulkan. And Vulkan is very fast because it's very hard. So to make a hello world in Vulkan, render a triangle, or count 1 + 1, you need about 500 lines of Rust or C type of language. But then Spiro5 has these very nice features, like it makes GPU code very fast. It has something called subgroup operands, and these are basically these SIMD operations which let you to add up to 1,000 numbers together in a single instruction. And then the interesting fact for the edge computing paradigm is that the Vulkan and Spiro5, they work on all platforms. So whether you're on AMD or NVIDIA, whether you're on desktop or mobile, it runs the same. So, and even now there's like web GPU support, which is something we will get into. But the point is that this Spiro5 thing might be the container format for GPU programs, which is something I want you to kind of maybe as a takeaway of this all. And then basically my thing has been doing this kind of like loop. So from Python to Cython to APL to Rust, and from Rust to Vulkan to Spiro5. And what I've been trying to do is a foreign function interface for Python. So my idea has been that maybe there could be like a way I could represent these kind of like in Python you would have APL. So in Python you would see APL, and that would magically be run on the GPU. And here are some initial benchmarks from yesterday. So when running a random forest prediction, which is not that hard to do, and 150 estimators on an array which is 6,000 to 300 trees, so quite small, scikit on Python OpenMP, so the native Python thing does it in 500 milliseconds, and CPU APL on something called dialog interpreter does it very slow because it runs only on one core and one thread. And then my thing of this compiler thingy runs it at 300 to 800 milliseconds using 124 cores. And then I guess like one thing is regarding this interoperability. So another project I've been working on is then this shows basically that you can run GPU code even on a web browser. So maybe an interesting remark about edge computing in general is that you can run these Peer 5 programs even on a web browser. And this is a project we did over the weekend with a friend of mine. And this is a website which is now live. It's called luskin.live. And it has an actual Peer 5 program behind it, which shows that you can even communicate these Peer 5 programs between different platforms. So regarding edge computing, this shows that it's very easy to even, with the current standards, to write an orchestrator to GPU programs and communicate the GPU programs. Even in here, it's only a sum addition. But anyhow, it's pretty easy to do this kind of system in which some very low performant device is communicating with the other one, and the other one is doing the actual computation and returning the results. And the final thing is that an interesting thing for the edge computing is this research regarding type theory of API. So normally API is dynamically typed, but it is possible using the current kind of like state-of-the-art type systems to statically rule out errors in API programs. And it's able to infer all of the types because API is very restricted. It does only arrays. So it's pretty easy to formally verify a lot of properties regarding API. And what this means is that maybe with some more work, we could achieve something which is called basically static memory management. We could see that when you are running, even before you run an API program, you're able to say that this program will take this much memory. And we can see why this could be very interesting for edge computing. Because if you have a program and you can say even before running it, that this program will at most use this much memory, it could be very good property for schedulation, because you could have guarantees that a program will not use more memory than what it says, and every party can check that. So finally, there are some links, and I think I'm running out of time. I'm over time anyhow. So for APL, you have something called try-APL. For WebGPU, you can see that GitHub repository. And then if you have some idea of a program you want to accelerate in machine learning, you can send me an email at that thing. And then I will be providing the links later in Twitter. And that's it. Thank you.
So thank you, Yusuf, for the talk. It was very interesting to see like work on very old programming languages which were to a large extent forgotten and many as such. And on this, one clarification question was which I had was, what was the reason why APL did not get popular in the 60s? Like you must have done some analysis on APL and its history. So were you able to get some pointers on like why it didn't work out in the past? Was it because parallelism was not present in the processing units such as PDP-11 and the VAX computers of the past?
Exactly. So APL kind of like by chance became very relevant language in the past 10 years, exactly because of the parallelisms. In 60s, you didn't have parallel computers, but now, by chance, you end up seeing that these languages, which were invented for a completely different thing, happen to run very fast on modern hardware, because at some point we had the problem that CPUs don't go through the Moore's law anymore, but they do something else. They increase in cores. And then we have more kind of like interest towards data parallelism than we have had before. And APL just happens to do it very well because it deals with very simple kind of like types which are very easy to mathematically reason about. And then, yeah, and then another thing which has been like APL have struggled with in the past is that basically APL was then, it remained a long time as a mainframe language. It was a language which was mainly run on IBM mainframes, because IBM was the company to which the Kenneth Iverson worked for, and that was the first place in which APL was actually translated into a programming language. And it never quite escaped that kind of industry. Before, just a few years ago, this Dialog company, which does, it's a proprietary interpreter, but it's free for academic use. So you can try it out by yourself to run kind of like the state of the art of APL now. But they only let people to use it for free just a few years ago. Before that, all APL interpreters remained kind of like this closed source and proprietary software. And regarding like low-powered GPU devices, high precision operations, I will have to see. I haven't had the time to check it out just yet, but that's something I want to work on, is that currently it runs on desktop hardware, but there's no reason why it wouldn't run on iOS or Android. So that is something I will work on next. But it does run on NVIDIA Jetson, so these ARM devices. So there's no problem with that.
Just a follow-up question on that. It's like, because APL has this nice loop-free property and which is useful for formal verification. I was just wondering if there is any ongoing work on strongly typed variants of APL.
There's some places that Oxford paper was something that was published 2017, so it's quite recent. But then there's another university, Northeastern, it's in Boston, and they have been researching strongly typed array processing languages. So it's, I cannot remember the name now anymore, but basically you can find that there is some research into strongly typed array programming languages, but not so much. It kind of like it would need to combine a lot of theoretical work, but that's something that I'm also interested to study later on.
So do we have any more questions to ask you, sir? There is one more question from Aditya Mehta from University of Ohio, and
yeah,
but he asked, can you just read the question?
Yeah, I can see the question.
Okay.
So yeah, no problem. That has been kind of in a state of debate, because APL has had for a long time things called reshape. Like reshape function was something that was named in APL, and I think that it hasn't been said that the NumPy authors would have said that these are straight from APL, but it's very apparent that NumPy and APL, maybe like you can think about NumPy as the modern way that APL is still living in our current systems, is that they basically work on the same principles, only do arrays, and they have these operations such as reshape and so forth. Yeah, so yeah, they are in some sense very, very similar, or at least related. Yeah, no problem. I guess I'm out of time, so I have to let someone else take it from here. So thank you for your interest.
Yeah, thank you for the talk, and now we can go to the next talk, which will be given